Lesson 7.5, modeling data. So let's look at some overall trends here. If you see a linear trend or say if two variables are directly related, say as x increases, y increases at a constant rate, you can find that slope, right? Quadratic, this looks like a parabola. All right, and then, exponential, we've been working on for about a week now, and that takes this type curve. Those are some main type curves you guys have seen, and this last one is due to this class. Okay. All right. A lot of this lesson has to do with like tables of values and making scatter plots. I'm going to pull up Desmos and do some of these with you guys. Okay. I'm looking for an overall trend. Like, can you find a curve of best fit? Okay. If you stand back and look at the data, maybe it fits one of these type curves. Okay. Before I jump in and do that, I was also reading, of course, your guys' Alex questions. Okay, so here I'll do some examples with you guys. Okay. um, that could help you out, not just with these book questions, but also with your Alex, of course. Yeah. Right, so what if you saw, right, let's say T represents the time you were driving on a road trip, or I'll call this road trip. Okay. So T is like the number of hours you're driving, and X represents how far you've driven. Okay. So at time zero, you're living home, you haven't gone anywhere. So maybe zero, zero could be a point. Okay. And then you get on the interstate highway, driving. And sometimes you stop and get gas or eat lunch or something, right? And otherwise, you're pretty much going for like 8 hours. You're just driving all day. Okay. And so you say, how far have I gone as time's been going on? You might get a scatter plot that looks something like this. Okay. So hour by hour, it's like how far have I gone overall? Like I'm watching the odometer go by on my car, right? So this doesn't make a perfect line, creates a like a scatter plot, right? But there is a like a line of best fit. A line of best fit looks like approximately like that. So I could make a table in Desmos, which I'll do some of these with you guys in a few minutes, right? And then figure out what's the curve of best fit. And I bet the slope of this line tells me my average speed. Like, oh, the average speed, including all your stops and whatnot, maybe it was like 45 miles an hour. Sometimes you're going 70 miles an hour on the interstate. Sometimes you stop for gas. Okay? It's like that. Right. Or another example I saw show up on Alex was, let me call this one heating bills. Right, heating bills, right? So what if T is the temperature outside, maybe in degrees Celsius, and then the x-axis is like I'll put a dollar sign, like how much money you spend on the heating bill. Right? So if the temperature was really cold outside, right? Like if it was like 10 degrees Fahrenheit, right? Then you probably spent a lot of money on your heating, right? But if the temperature was like, oh, like 70 degrees Fahrenheit, so pretty mild, well, maybe you didn't really use the heater at all because at that point it wasn't really necessary, right? Maybe one day you felt a little chilly or something, so you turn on the heater just for like a little bit, right? Okay. And then what about the temperatures between, say, like 10 degrees Fahrenheit and 70 degrees Fahrenheit? Well, as the temperature would rise, let's say if you're going to the right, you tend to use the heater less and less and less. Okay, so you might create a scatter plot that looks approximately like that. Okay? So as the temperature would rise, your heating bill would decrease because you're not using the heater as much. Okay? How can I name these curves, by the way? Okay? So this first one I can call some kind of direct or linear relationship. Okay. This one, well, this is also linear. It looks like my scatter plot. I could use a linear relationship, but it does have a negative slope. So in physics, we usually call this inverse relationship. Okay. You can also call this a negative correlation. Okay. I'll spell that out here too. Negative correlation. Right. As the temperature increased, the money you spent on heating decreased. One variable increases, the other decreases, and vice versa. Right? One goes up, the other goes down. Right? Whereas driving on a road trip, I would call the relationship between how far you've driven and how much time you're driving for. I'd call that a positive correlation. Like if you had some friends and you called up one friend and said, oh, I was only driving for 2 hours, you could infer that he hadn't driven very far. If another friend said, oh, I've been on the road for 9 hours, you could infer he probably made it a lot further than your friend who only drove for 2 hours. I know. What about some of these other type curves? Oh, here, probably. Here, can I come up with examples for these other ones? I think so. Okay. How about you go to the edge of a cliff and you drop a ball? You say, how far did the ball fall? How far did the ball fall off a cliff? Okay, as a function of time. Okay. So maybe this time maybe it's a really, really tall cliff. You go to the Grand Canyon and it takes like 10 seconds for the ball to hit the ground. So you can scale this up to 10 seconds. Okay. And how far did the ball fall? Right? And you have some way of getting that metric. Right? Maybe there's a little air drag, so it's not a perfect correlation here. But at time zero, you're just releasing the ball. It hasn't fallen anywhere yet. Right? Actually, to get rid of air drag, this does make a perfect parabola. Right? But if you count for other variables, maybe it kind of gets blown around a little bit. Right? Maybe you can still approximate this sort of a parabola. Right? So maybe something like this. Actually, again, the physics class I teach that those would line up in a perfect parabola if you drop the ball in the vacuum. Okay, okay, so yeah, so this would be some kind of well, parabola shape. I'll just spell out the word parabola. Parabola. But if you do like how I'll do height drop like as a function of time. Okay? And well, I need to bring in an exponential. So an exponential, you guys seen a couple times recently, is Moore's law. Moore's law. Right. How many transistors can you fit on a computer chip as a function of the amount of time going by? Right. Let's say you start back in like 1950 or 1970. So we're going way decades back, way decades back. Okay. And then say in 1970, maybe you could fit so many transistors on a chip. But 1970s computers, you're big, clunky. Okay. You know, you'd have to like fill a whole room the size of this classroom just to do what you guys can do holding in your hand, right? Actually, what you can hold in your hand with your smartphone is like way more powerful, almost certainly, than the computers we're using to send astronauts to the moon back in 1969. Anyway, so the time is passing, and if you treat this as linear, this actually would make an exponential curve. Right? It takes off real fast. It gets real steep. Okay, so as long as both these axes are scaled linearly, right, then this creates a classic looking exponential curve. Exponential. Okay. All right. So there you go. So there's examples of four different types of relationships you can see. I attaches some stories to those. Okay. And a lot of examples in this lesson involve looking at scatter plot data. So let's do that. Okay. Here, I'll do exactly what I have here. Right now, they give you a table. Right. They tell you how to plug these into, I think, like a classic graphing calculator, like a TI-83 or something. Right? If you have a TI-83, ooh, I have one here. Right, somebody left this one. Right? You could totally plug it in. That's fine. Here. I'm just gonna pull this up on Desmos and show you guys how to do this in Desmos. Right, okay, it looks like I tried this out before. So let me clear all this out, show you guys what I was doing here. Right, so type the word table, T-A-B-L, and then as soon as you hit E, bam, gives you a table. We did this last semester, by the way. Okay. Now I'm gonna copy down these values from the book. So your book gives -5. I'm copying this straight from page 38. X is -5, -4, -3. Does this -2? Oh yeah. Okay, so it goes all the way to +4, and Desmos very conveniently picked up on the pattern, so it just goes by integers. Okay. Now the y values. Now here's where it's going to be a little scattery, or I think it will be. We're going to find out. So -3, -2.7. Here, I'm going to pause this video and just type the rest of these numbers in. All right, so I got all the points plugged in. Right, there's the graph, what it looks like. Right. Yeah, I would guess just by looking at the scatter plot that there's some exponential curve that fits that. Right, you guys see that? Some exponential curve. All right, and what okay, so let's make an equation with this. Right? Now, how you can create a curve of best fit is you type y subscript 1, right? And then right arrow key, so get out of the subscript, then hit the tilde, and you do shift to get the tilde, right? And I need something to do with like e to the x here. Now, if I just start with that, this is probably not going to create a very good curve, but let me just show you guys. E to the x. Well, here if I yeah, okay. Right. But I think maybe this E is not necessarily the perfect base to fit those points. So I'm going to let the Desmos come up with that. Also, there might be some vertical stretch factor in front of that. So I need to come up with all that. So I'm going to say A times, okay? And then I'll let the computer come up with some base. So base to the power of X. Okay? But one more thing is usually these exponential curves, they'll see subscript one. There you go. Right? And then hit right arrow key. Let's get out of the whole, all that, right? Do you guys see how there's a horizontal asymptote here at the x-axis at y=0? Right? But the scatter plot data looks like it's definitely a few units below that. So over here, I'm going to say plus C. Right, let me come up with that too. Yeah, there you go. And that green curve of best fit, that fits that data really nicely, doesn't it? Doesn't it? Yeah. Right, and Desmos tells you, okay, it's best it could possibly fit. This R squared being very, very, very close to one means that this worked really nicely. Okay? So there's your A, B, and C that correspond to that expression. Okay? So if you wanted to say, what's the base of this exponential curve? Well, that's the B value, 1.75 about. Okay? What's the vertical stretch factor is about 3.72-ish. Okay? And there's a horizontal asymptote here at about y equals negative 3.26-ish. Yeah, so if I wrote y equals, let me go ahead and do that. Can I make another equation? So y equals negative 3.26. This should represent the horizontal asymptote. Yeah, it sure does. That blue line represents the horizontal asymptote of that green curve. All right. So one down. Got that one. Wink. All right, next one. Example two. All right, so same thing. Got scatter plot, and what can we make out of this? Okay, so we type all this data straight off page 39 into Desmos. Straight off page 39. Okay, so go back to Desmos and clear all this out. Clear. Actually, I wonder if I just leave this here. No, I think it's a different kind of curve. It's probably not going to be exponential. So we clear all this out. All right, so let's get rid of all this. Table. The x values go 5, 10, 15, 20. 5, 10, 15. All right, yeah. Desmos picked up the pattern. Goes up to 50. There you go, up to 50. Okay. And then the y values. So 65, 140. Same as before, I'm going to pause this video and pop all those in for you guys. All right, so I got all the table values plugged in straight from page 39. Now, the scatter plot definitely looks like a parabola, but it looks like a really skinny parabola. Now, I can fix that. I can go to this wrench tool, and here I'm just going to make the x-axis a lot wider. Okay, so x-axis, let's go from like negative 10 to 60, I think should contain the data. All right, whoops, 60. All right, let's see if that looks a lot better. Oh yeah, yeah, that looks a lot better. Okay. That looks a lot like a parabola. And if I suspect that's a parabola, that would, well, the parent function would be y equals x squared. So how can I model that? It's going to say y underscore 1, then right arrow key, get out of the subscript. Let's do tilde. So yeah, shift tilde. Okay. Now there could also be some vertical stretch factor, so I'll represent that with a and let Desmos tell me what a is. And then multiplied by if it's an upside down parabola, well, the fact that it's some kind of parabola, I need to have x to the power of 2, x squared, right? Uh, now, one more thing. This is shifted to the right, and there's a few ways to shift this to the right and up. One thing I can do is I can do open parenthesis. Instead of saying x squared, I could say x minus b, right? And then square that collectively, so it'll shift it to the right. Oh, I do need to do underscore 1 on the x. Okay. Um, X minus b squared, and then plus c. Look at that. Look at that. Okay. So, all right, so that's like the best parabola you could fit to that scatter point data. Okay. So x1 is your x value, your horizontal axis variable. Y1 is, of course, the y values. Okay. This minus b tells you how much is shifted to the right. Now just eyeballing the graph, it looks like it's shifted to the right. What, 22.2? That's exactly what this says right here, 22.2. Okay. And this plus c value tells how much it shifted up, which looks like about 185. Yeah, there it is, 185 right there. Boom. Okay. Now this a represents like the vertical stretch factor, tells you something about like stretching the parabola basically. Okay. Oh, and also see how a is negative? That also turned the parabola upside down for me. Now, if I put in the negative myself, let's see what would happen. Boom. All it did, the equation looks the same, except a turned back positive because I'm making the negative myself. Right? If you don't include the negative, boom, then Desmos comes up with the negative for me. All right, so there you go. That's about all there is to that. All right, let's see what's the next example. Look over here. Okay, so we just did this one. So I wonder what this one looks like. Yeah, let's do the whatever this is down here. We're gonna find out. All right, so back over to Desmos. Here I'm gonna clear all this out. clear this out, type table, and the x values go 0, 1, 2, 3, all the way to 7. 0, 1, 2, 3, all the way to 7. All right. Y values. All right, so I plugged all the data in. I did also go to this branch and I adjusted the x-axis so that it fits nicely. Actually, that does look like another parabola. Maybe that's part why they included this in example two. I'll go ahead and do this real fast anyway, though. Let's do y underscore 1 and then tilde. And I'll type in the same expression I had before. A times, let's see, in parentheses, x underscore 1. And then I'll say minus b in that raised to the power of 2. All right, and then the whole thing plus c. Yeah, there you go. There's a nice parabola fit right there. It tells you what a, b, and c are. You can plug in a, b, and c to make that expression. All right, go on to the next one. Next one. Point. All right, what is this? Use a data model. Right, so 40 years since opening their first shop, a popular coffee company grew to over 17,000 locations worldwide. The table shows number of shops since the company began. Use the model to predict the number of shops 10 years and 42 years after opening. So 10 years is, well, closer to the beginning, and 42 years is just after the data ends. So it went from year 0 to 16, 18, 20. And so, okay, so we've got all these shops, right, year by year by year. It goes up to year 40. Right, there's 17,000 in some shops at year 40. Right? And so we'll plug in that scatter plot data and then see what from there. I wonder what shape that's even going to look like. Right, got to figure that out. It's probably not a parabola, so I'll go ahead and just wipe that out. Let's go table. Okay. Now, uh, okay, so first value was 0 years after opening. Then it went 16, then 18, then 20. Desmos is not picking up on the pattern. All right, so I'll have to type in all the x values. All right, there's all the x values. So it goes 2 years at a time, except that it skips a bunch of time near the beginning. Okay, the number of shops. Well, there was one shop. Maybe there was only one shop for like many, many years. Then after 16 years, they got up to 17 shops, then 55 shops. All right, so got all the shop data put in. Let's go adjust these axes. Let's have x go up to, let's say like 45, right? But the y values should definitely go all the way up to, well, we got 17,000 shops. Let's go 20,000, right? See if all the points landed here. Yeah, I thought about, oh, ooh. Right. Now, this looks like a logistics curve. Hmm, logistics curve. Remember, I think I can remember how to make one of those curves. All right, I think I found the model here. Let me see. All right, so I typed in logistic curve model. Right, yeah, you guys see an S-shape looking curve? Right, that looks like that scatter plot data, doesn't it? Right. So here, one of the first hits is Wikipedia, and it shows this basic expression right here. Now, here, I might change that by throwing some factor in front of this E maybe, but let's type this in and see what happens. We're gonna see. So L over, now instead of L, I'll just call it A. Instead of, let me try 1 plus, and then base to the power of, if I have to go back and change that 1, maybe I'll change it to something else. Um, Basically KT. Right, so let's call it CT. Right. Well, whoops, not T. I need X. So let's do X subscript 1. It look like that. Hang on. All right, there you go. There you go. That's it. All right, so we'll show you guys how this logistics curve works. Right. So it's where a lot of times you might see this like population growth inside a petri dish, where you start with a few bacteria, right, and they start up and look like something that actually does look kind of exponential, right? But then when they consume the resources in their environment at the little petri dish, then well, the population kind of levels off at the end, right? Now, how does this model describe that? Right? So here I'll show it straight from Wikipedia here. Right? In the numerator is just a solid number, which represents the carrying capacity. Here's why that would be the case. If you let this x go to like infinity years, whatever, each of the negative infinity basically becomes 0. So 1 plus 0 would be 1. L over 1 would represent, hence the carrying capacity. And on this model, it'd be like, looks about 18,000 or so, something like that. Oh, actually, it tells me right here. It's 18,809. That takes the place of that A. Right, and let Desmos figure that out for me. Right, right, and then you also need a way for it to start off at basically zero. Right, so so all this exponent stuff. So x is basically the time variable or whatever the x-axis variable. Right, right, but the k, the x naught, just let Desmos figure that out, right, and it will create exactly this S-looking curve for you. Right, so there it goes. Right, just like that. Okay. Here's your logistics example. Logistics. Right. Okay, so that was a fancy one. Right. All right. Here, I just picked a couple of examples out of the main text because all of these are pretty similar, right? So you type the table either into your calculator or into Desmos. You say, what kind of curve should that look like? And then um, use this model to create the curve of best fit, right? And the factors you don't know, just call them A, B, C, and D, and so on, right? And so let's clear all this out. And I'm doing number 4 from page 41. So type the word table, right? Then it's like going -4 to -2 to, yep, 0, 2, 4, 6, 8, and 10. Right, and then the y values go 50, 32, 15, 0, -18, -30, -55, and -70. Okay. Okay. Well, I had this graph left over from last time. So let's change the x-axis from, how about -6 to +14. Okay. Now let's change the y-axis from, how about -100 to +100. Okay, I think that will contain the data. Yeah, it looks pretty good. Oh, that looks pretty linear, doesn't it? Looks like y equals mx plus b. I'm going to treat that as linear. All right, so I'll say y_1 and then tilde. Let's call it ax_1 plus b. Yep, looks like a straight line. It tells me exactly what are a and b. Yeah, scatter plot, line best fit. Boom, done. That looks pretty good to me. Pretty good. Right. Right. So I have not worked these out ahead of time, so a lot of these curves could look like anything. Actually, if you know a story attached to a lot of these, then you might be able to guess what some of the shapes might look like. Right. But of course, I did a bunch of examples here. Like this one was logistics. Right. I did a parabola with you guys. I did an exponent with you guys. Right. This one was straight linear. That's pretty straightforward. Right. So I wonder what this last one's going to look like. Oh, we got Brittany deposits $1,000 into an account and she's looking at her balance after 10 years. Now, it's possible that she just leaves the account alone and just lets it grow, in which case this curve should exactly match an exponential curve, growth curve, right? Or maybe it's also possible maybe she's sometimes putting in a little extra money or taking out a little bit of money, so which can create a more random like scatter plot. We're going to find out. So basically create this model and figure this out. So let's do that. So back over to Desmos. All right, clear this out. Clear this out. Type table. Okay, and we're looking at years 0, 2, 4, 6, 8, and 10. And then the amount in her account, she started off with exactly $1,000. Then after 2 years, she has $1,068.50. Then 1155.55. Year 6, she has 1265.25. Year 8, she has $1,400.35. And year 10, 1560.85. All right. Okay. I definitely need to fix my axes. Let's go x-axis. Well, we really need 0 to 10. So maybe I'll change that from like -2 to 12. Should definitely fit in there. Okay. And the y-axis, well, I got to go up to $1,600, right? So let's go -100 or so. That looks pretty good. And then this should be, let's go 1,600, I think, right? That, yeah, yeah, okay. That looks like it, okay, wants to be an exponential growth curve, or it could be, right? Now I know it's taken off real shallow here, but maybe it's just a small interest rate. Maybe that's what we could figure out. We can figure out what's the interest rate. Yeah, let's do that. So I'm gonna say y under, whoops. Underscore one. Okay. Right arrow key, tilde. How can I model exponential function? So something to do with like some base to the power of x. So let's do the principal. So the principal, I wonder if I can just type P for principal. I wonder if it'll get that. We're gonna find out. If it doesn't, I'll go back and change that to A. Okay. So one plus the interest rate, all to the power of however much time. One plus the interest rate, all to the power of, so T underscore one. Okay. No, I didn't really like that. Right. What if I change this to A and B? Change this to B and change this to A. Does it like that? Do I have to make this X? Oh, I do have to make this X because this was X1 up here. Call this X1. Okay, yeah, it created one for me. Can I change this to P? Can I change this to R? Yeah, it sure does. Sure does. So P is principal. Now, what does it estimate from that? Okay, now interestingly, this curve, even though it models it fairly well, it doesn't match it exactly, right? Which tells me that, yeah, she was probably sometimes pulling a few dollars out of her account or sometimes putting in a few dollars. Maybe. Looks like these middle years looks like maybe she was withdrawing a few extra dollars. And this last year looks like she put in a few extra dollars beyond what this exponential curve would predict. Okay. But here it's somebody, the principal is, approximately $975 or something, which it was really close to, right? It's about $1,000. Okay. And the interest rate we're looking at, well, the best we can say is predict the interest rate looks like about 4.7%, doesn't it? About 4.7%. Yeah, I think that would be the interest rate. So there you go. So now you guys have seen lots of scatter plots that you can pop into Desmos and it will craft the equations for you, right? In this case, P and R, fill those in for me. You can call it A and B. I'll give it to you. All right, and that's a wrap on the entire module 7.